All right, now we're moving on to simple harmonic motion and more generally oscillations, things that repeat themselves. Oscillations, and we're going to focus particularly of motions in one dimension. These sorts of oscillatory motions really pervade everything we do. There are oscillations going on everywhere. At the deepest level, some people argue that, the existence of matter itself is really just the oscillations of a bunch of little strings that are oscillating around back and forth, vibrating. But even in the macroscopic world, right, string theory aside, even in the macroscopic world, oscillations appear all the time. The fact that I'm sitting on this chair right now is deforming the chair a little bit. Now, if it's a rigid chair, I might not be able to see it that well, but with a cushion, it's very easy to see that there's a deformation that's occurring as the chair changes shape to support my weight. And then if I were to stand up, that change then is restored back to its original location, like a spring. A spring deforms as you squish it, but the more you squish it, the more it tries to get back to where it started, such that when you release the force, the spring goes back to its unstretched length. So just, pushing on this table right now, if I push on this table, I cannot see the table deforming, but it is deforming ever so slightly. You can think of molecular bonds that create solid objects. As just there's trillions and trillions of little springs that make up this table that all have exceptionally high spring constants. So I don't have to deform it that much in order for there to be a significant restoring force. If I push down, all those springs go down a little bit. And particularly if I release my hands quickly, it might be that they oscillate a little bit, right? And then there's some dampening, some friction that then settles them down to some sort of stationary state. But nonetheless, there are oscillations going around. So these simple harmonic motion, or let's just say oscillations in general. Oscillations occur as the result of a restoring force. And these restoring forces are forces that work against the displacement that is happening. If I push the table down, there's a restoring force that points up. If I squish the spring, there's a force that wants to unsquish the spring. Right? So these restoring forces, I should say, that want to return the object to equilibrium. In general, though, forces can be quite complex. We focus on the ones that are quite easy to write down, but a general force, my hand pushing down this table, is a quite complex function. So in general, we can ask what's going on in the simplest case for a general force. In general, the force is complex looking. But if we take it to be sufficiently well behaved, I know I can then always expand this force, no matter what its weird, complex functional form is. I can always write it as a Taylor series. So if we expand F, I'm going to drop the arrows now because we're going to just assume it's one dimension. Assume F, or let's expand F about x naught, which is going to be the equilibrium position. I can always expand it around whatever point I want. Then f sub r is going to look something like, and if we're going to one dimension, I can actually get rid of the f. Let's replace it just with x. And that's going to be F at the equilibrium position plus first derivative evaluated equilibrium position, right, x minus x naught, plus 1/2. Then you got the higher order derivatives, etc. Now, for sufficiently small displacements, where we can simplify this, is we can ask ourselves, what if I only displace something a little bit from equilibrium? I push down this table a little bit, so it's a little bit displaced from equilibrium, and then I let go. Or I push down on a spring a little bit, and then I let go, and then it wobbles back and forth. So we can make some approximations, right? For sufficiently small displacements from equilibrium, we can assume it's so small that things like x minus x naught squared is approximately 0. To the third power is even smaller, to the fourth power, etc. So I'm essentially approximating that I can drop all those higher order terms. Equilibrium implies that F evaluated at x naught equals 0. You can think of this as just one force acting on the object, that's where it vanishes, or if this F represents the net force, that's where the net force vanishes. Again, by definition of equilibrium, that there's no reason for it to move if it's at the equilibrium point. So then it looks like f of x is approximately whatever the first derivative is, evaluate the equilibrium point, times x minus x naught. And then if it's a restoring force, remember that derivative, it's the derivative evaluated at a point. So that thing in parentheses is just a number. Right? So this, in a sense, is just a number. Whatever that force value is, that derivative value, when you evaluate at the equilibrium point. But we can say that it better be, whatever it is, it better be negative. Doesn't make sense for it to be a restoring force if it's positive, because that means a little bit of displacement would cause the force to want to push it even farther away. So we want it to definitely go back. So let's just replace, since it's just a number, let's just replace that derivative as negative times k, right? Negative times some constant. And then it's x minus x naught. And that is the approximation of a restoring force for a sufficiently small displacement from equilibrium, which, notice, is nothing more than just Hooke's law. You move a little bit away from equilibrium, there's a restoring force that wants to pull you back towards the equilibrium point. And we've worked already that this sort of force that takes this form is a conservative force, where you can write the potential energy as 1/2 k, that displacement squared, which is then the potential for what I'm going to call elastic oscillators. Right, because if this is the way that the net force, or if this is the only force that's acting on the object, takes shape, you can work out that it's a conservative force and it has this particular functional form. If you add things like dampening or driving, maybe something's pushing on the box attached to the spring, right? Or maybe it's something like, a driving force could be you have an oscillator that might be a kid on a swing. A driving force might be that you push on the kid at certain points. Maybe you push on the kid at random points, or maybe you always push on the kid at the same exact point. And that could be an example of a driving force being applied to an oscillator. In that case, kind of like an oscillating pendulum. But we will save that for the next module, or a couple modules from now. So we expect these solutions to be sinusoidal-like, right? Maybe even sinusoidal. So let's take, of course, the simplest case of a 1D box attached to a spring. The spring is a constant spring constant K. The box has mass M. The table is frictionless. Everything is horizontal. The horizontal equation of motion then says that mx double dot is going to then equal, and I'm going to put, to simplify my life, I'm going to put the origin at the location where the spring is neither stretched nor compressed. So then the spring force just looks like negative k times x. Because where x equals 0 is where that force vanishes. This then can be rearranged to look like mx double dot plus kx equals 0. I might divide through by m. So I have some constant k divided by m. I know that as a constant because it's the ratio of two constants. I could ask what units are going on here. Well, I know k times x is a force, so k better be newtons divided by meters. Mass is then just kilograms. A newton is kilograms times acceleration. So then this looks like it's acceleration times 1 over meter. So this looks like at the end of the day it has units of 1 over second squared. That could be an angular acceleration, or it could be an angular velocity squared. It's only 1 over seconds, then you're squaring it. And since I know what the answer is going to be at the end of the day, that's actually the form that makes the most sense given the solutions. So we're going to write that as, we're going to replace k over m with omega naught. Omega naught then having units of let's see, omega naught is then going to be the square root of this thing. So omega naught squared is k over m. Omega naught then has units of 1 over seconds, and we'll see it does play a role of an angular velocity at the end of the day. This expression is the simple harmonic motion equation. In that objects that obey this differential equation for its trajectory undergo simple harmonic motion. The solution ends up being sines and cosines, which we'll show in a second. But the nice thing here, the thing to take away, is that this is a very simple differential equation, which in this case represented the 1D motion of a box on a horizontal plane. But the takeaway, since a differential equation, right, that's just math, is that if I write this as x double dot plus omega naught times x equals 0, or if I write it as theta double dot plus omega naught squared theta equals 0, or if I write it as star double dot plus omega naught squared plus times star equals 0. No matter what is going on in the system, if your differential equation at the end of the day looks like a second derivative plus a constant squared times the position or times the variable equals 0, that's simple harmonic motion. We'll see this for pendulums, we'll see this for boxes attached to springs, various different types of objects, but if you can write it as that the second derivative equals negative a constant times the variable itself, right? Like x double dot equals negative omega naught squared times x, then that is simple harmonic motion. And so whenever you see that pop up, if you can write the second derivative as negative a constant times the variable, you know you have simple harmonic motion. It's a good thing to ingrain in your mind. Whenever you see that equation, light bulb should start going off, horn should start blaring. Simple harmonic motion. But how do we solve this? In a differential equations class, you probably have already gone through this, but we can just remind ourselves. Right, this is a second order differential equation because the highest derivative is the second derivative. It is a linear differential equation, meaning that every term has either x or one of its derivatives, but never a product, never anything in the denominator. There's no x times x dot. There's no x dot divided by x. There's no x double dot times x. There's no x squared. This is a linear differential equation. Also, in this case, a homogeneous differential equation, which means it is set equal to 0. There is no additional, right? This is ultimately solving for x as a function of time. That right-hand side could be a more complicated function of time, or could even just be a constant. Since it's equal to 0, this is in a homogeneous differential equation. So we expect two constants of integration when we solve this. Unsurprising, since Newton's laws of motion are also second order differential equations. We always require two pieces of knowledge, right? Usually we need to know a position and a velocity in order to uniquely solve the differential equation. Same thing here. We expect that we need two pieces of information, which is typically your initial velocity and position. Since this is a linear differential equation, we know that the solutions to this differential equation should have a variety of properties. Particularly, we know that they should obey homogeneity, where if x1 is a solution, which again means I can plug x1 into this equation and I don't get nonsense, then c times x1 is a solution, where c is a constant. If x1 is a solution, 3 times x1 should also be a solution. 5 times x1 is also a solution. 1 over pi times x1 is also a solution. We know the solutions should obey linearity. If x1 and x2 are solutions, then x1 plus x2 is also a solution. All right, I should be able to add or subtract. Well, let me get to that. I should be able to add two solutions together, and they are also solutions. And then they also should obey some linear independence. Where, and this is essentially just combining the previous two results. If x1, x2 are solutions, then c1 times x1 plus c2 times x2, where c1, c2 are constants, is also a solution. There's also some requirements on kind of how these things are, other properties that these have in order to be something called linearly independent. But essentially, it's that you can add sums and multiply by constants, and those are also solutions to differential equations. There's also particularly a uniqueness theorem that is very important, where at a given point, as long as the solution and its derivative is well behaved at that point, which includes things like continuity, for example, then you can say that that solution that goes through that particular point is unique, and that you don't have to worry about there being some secret solution that once you have found the solution for those particular initial conditions that goes through a particular point, that is the only solution that has those particular initial conditions and goes through a particular point on the number line. Which actually is very powerful and is perhaps something that isn't quite fully appreciated, even though you've been using it all the time. We've been constantly solving for the motion of an object, and we get like a trajectory. I throw an apple into the air. I know that that solution is parabolic. And we always just took then as an assumption that all motions of apples thrown in air are parabolic. For different initial conditions, it changes the exact parabola, but for a given set of initial conditions, the shape is kind of parabolic in shape. We never once contemplated the possibility that, well, maybe, on Sunday afternoon at 3 p.m., the solutions aren't parabolic, but they're actually sinusoidal. We never assume that maybe there are cases where if I go, off and do this in France, then I'm going to get a completely different solution. We always just assumed that everything was parabolic. We assumed that there was some uniqueness to the solution we were obtaining, which is, again, that is very helpful in what we're trying to do. That once we find a solution that obeys your initial conditions, you can say you not only have you found a solution, you have found the solution, which is usually derived and proved probably in a intro differential equations class. But very, very helpful. Even though you might not fully appreciate that we were doing something like that. In general, particularly we were solving a differential equation that had no first derivative in it, right? We were doing x double dot plus omega squared times x equals 0. In general, we'll see the equation actually looks something like this, where if there is a first derivative, it might look something like this, where there is an additional term where there's this 2 times beta, and beta is also a constant. We're going to call it the dampening constant. So this is particularly when dampening is present. I never remember if it's dampening or dampen. I guess then this case is dampening. Yeah. When dampen is present. Again, we're not going to worry too much about this beta. We're going to let beta equal to 0. But let me talk about this super generally now before we do some examples. So what is the approach? The approach is that you assume the solution looks something like e to the r times t, where r is some constant. You plug that in to get an auxiliary equation where the differential equation then becomes r squared plus 2 beta times r plus omega naught squared times nothing equals 0. That is a quadratic equation where then you get 2 values of r. Right, it has 2 solutions when you solve for the quadratic equation. And then you write the general solution as some combination of exponentials that use those 2 possible values of r, because these are 2 values of r that when we plug e to the rt into that differential equation, it's satisfied. We throw in some constants out front to let that, that can then be matched by the initial conditions, and then we're done. But remember from the quadratic equation that there are kind of 3 cases that can arise, and you have to consider each of those cases differently when you're solving the differential equation. So there's the case where R1 and R2, which I'll take to be the two possible solutions, I guess you just write it out over here. R sub I is then negative 2 beta plus or minus 4 beta squared minus 4 omega squared, all divided by 2. And notice, you might ask, why is it 2 beta out front? Well, it ends up, we'll talk about it, it's actually just a convention, because notice now there's a 2 everywhere. Square root of 4 is 2, so that I can simplify this to be beta plus or minus beta squared minus omega squared as my two possible solutions. So there are three possibilities. There's the case where R1 and R2 are both real and unique or distinct. All right, so the quadratic equation gives me two real numbers, 3 and negative 3 or something like that. Then the solution is x of t is a e to the r1 times t plus b e to the r2 times t, whatever those two solutions are. A and b are your constants of integration. R1 equals R2, and they're both real. Notice that occurs when that square root thing goes to 0. So you got two real numbers, but they're both unique. Then, to ensure linear independence, it's a times e to the rt. Right, they're both the same, so I'm not going to bother with subscripts, just r. Plus, but then you do b t e to the rt. And you can work out that t times e to the rt is also a possible solution in this case. So that's kind of the case where the square root goes to 0. And then you have the case where they're both unique but complex. In this case, the square root thing, right, the thing inside the square root goes negative. In this case, r sub I looks like it's going to be negative beta plus or minus some number times the complex number I. I'm going to write this as r can be written as kind of gamma plus or minus delta times I, where gamma and delta are real numbers, and then there's the square root of negative 1. Well, in this case, the solution is still a e to the r1 times t plus b times e to the r2 times t, but the r's themselves are now complex numbers. And I'll let a differential equations class go through the work. For here, it's useful to use Euler's formula. Where e to the I times something, should have given myself more room. E to the I times something is cosine of that something plus I sine of that something. A deep connection between exponentials of complex numbers and the trig functions. Something interesting is going on there. To get the solution, where in this case, there's kind of multiple ways you can write the solution. One way is to write it as if there's an e to the gamma t out front, and then there's, instead of exponentials, it's cosine and sine. So a cosine of delta times t plus b sine of delta times t. Just remember that there's this exponential out front. Or the way I think is actually more useful, rather than using a and b, I'll now use c and phi, or it can be written as c, some big constant, times cosine of delta t plus some phase angle phi. And let me highlight the constants. So a and b are the constants up here, and then c and phi are the constants there. Or those are what's matched to your initial conditions. And of course, the A and B and C and phi are all related to one another. But again, who cares? We're just matching these things to our initial conditions. I particularly like the second form better. I think it's more useful to think of just one trig function, because I can imagine easily one trig function, though the sum of trig functions also can create something that looks like just a single sine or cosine, which you can prove using trig identities, which is exactly how you prove that these two lines are equivalent to one another. All right, the addition and subtraction rules for trig functions, you can turn the first equation into the bottom equation. So that is the general case for solving the homogeneous differential equation. If instead you had something where here's this, but then it was equal to some function of t on the right-hand side, where this is non-zero, and that might represent, say, some sort of driving force that's being added, an additional force that's being added. But this is not a homogeneous differential equation anymore. However, all hope is not lost, because it turns out that all you have to do is you still solve the homogeneous case. To get, I'll call it x sub h of t. Right, that's the thing we just did above. Find the auxiliary equation, and it's either exponentials or trig functions. But then you just have one more step. Also, guess or cleverly find a particular solution, I'll call it x sub p of t, such that when you plug in just this particular solution, so you get x sub p double dot plus 2 beta x sub p dot plus omega squared x sub p. And when you plug that in, what you get at the end of the day, once you simplify things, is that you get the right-hand side. A solution that when you plug it in, you get the right-hand side. The homogeneous equation, remember, the homogeneous solution is when you plug the thing in on the left and you get it equal to 0 on the right-hand side. But the nice thing is that the full solution, x as a function of t, then is the homogeneous solution plus the particular solution. Then you just add the two together, and you're done. Because again, remember that the homogeneous solution, we expect our answer at the end of the day to have two constants of integration, right? The homogeneous solution, remember, has the two free constants. So you could ask, are there any constants of integration in the particular solution? Well, no. It should be an exact solution that when you plug it in, you get that exact right-hand side, which presumably did not have any arbitrary constants in it. It's just some function of t, f of t. So you're not introducing any new variables or free constants that are flying around. It's just you have the two constants of integration that's in the homogeneous solution, and then you have the one particular thing that satisfies the right-hand side. And that overall, again by the uniqueness theorem, is your true full solution for the entire thing. All right, let's end with a couple examples. Suppose my differential equation is x double dot equals 3 times x, with the initial conditions that x at 0 equals 0 and x dot at 0 equals 1. Well, this looks like, if I move the 3x to the other side, it looks like x double dot minus 3x equals 0. This is linear, it's homogeneous, so I don't need to worry about particular solution. And get my auxiliary equation, where I assume the solution is e to the rt, and then this becomes r squared minus 3 equals 0. then that becomes that r equals plus or minus the square root of 3. So then I assume that, or then I can anticipate that my true solution is a e to the square root of 3 times t plus b e to the negative square root of 3 times t. My two values of r, each of them get their own exponential. They're both real, they're both distinct, so it's just the sum of exponentials. The derivative in this case, if I need it, looks like it's going to be e. It looks like it's going to be something very similar, with an overall square root of 3 out front. So then I got to figure out my a and b. When I plug in t equals 0 for x, looks like I get a plus b. And based on my initial conditions, I'm told that that equals 0. That's from this right there. So then that looks like it implies that a equals negative b. Then when I plug in 0 for the first derivative, looks like I get a minus b times the square root of 3, and that better all equal 1. But then since a equals negative b, it looks like in this case a then is 1 over 2 the square root of 3 at the end of the day. So then that b is negative 1 over 2 square root of 3 at the end of the day. And my full solution is 1 over 2 square root of 3 e to the square root of 3 times t plus e to the negative square root of 3 times t. There should be a negative sign, right? Because b has a negative out front. And that is my true solution. I could plot that. That is the answer to this particular differential equation. It might be nice to use some fancier math and know that I can write this as not sine of square root of 3 over t, but the hyperbolic sine of square root of 3 over square root of 3 times t. Where if you haven't seen these before, there's the hyperbolic trig functions. Let me see, I'll use t, where the sinh of t is 1 over 2 e of the t. Let's see, and sine is the negative sign. And then there's the hyperbolic cosine of t, which is 1 over 2 e of the t plus e to the negative t. And these are trig functions that are defined not on a unit circle, but they're defined on a unit hyperbola. But they still have some similar properties like the trig functions. Like notice that the derivative of sinh is cosh. But then the derivative of cosh is not negative sinh, but it's just sinh. So they do go back and forth, kind of like the trig functions, though they're not exactly identical. And they have a lot of similar properties to the trig functions. But they're defined on a hyperbola instead. And they're really just the sum and differences of exponentials. So they don't oscillate like trig functions. Nonetheless have similar properties like the trig functions. Again, like Euler's formula, there's something interesting going on between exponentials and trig functions. All right. What about if the differential equation instead was this? So x double dot equals 3x plus 2 with the same initial conditions. Well, then if we solve the differential equation to put it in the right form, notice it's x double dot minus 3x, same thing we had before, but equals 2 instead of equals 0. So this is a non-homogeneous differential equation. So we have to solve it in 2 steps. We have to first solve the case where it is equal to 0. That's the homogeneous case. But that's nice because we just did that. Right, and we said that was 1 over the square root of 3 sinh of the square root of 3 times t. And then we have to solve for a particular solution where when I plug in this particular solution, I get 2 on the right-hand side. And this usually just comes from practice and some intuition. Polynomials are usually good first guesses. In this case, that's something where I'm going to take its second derivative, subtract from it 3 times the original function, and I get 2. Since 2 is a constant, it's pretty easy to imagine that the solution negative 2/3 would work. I take its second derivative, that just goes to 0, so who cares? But when I multiply this entire thing by negative 3, I get 2 at the end of the day. So then my full solution is the homogeneous solution plus my particular solution. Oops. Minus 2/3. And that is the full solution, right? It's the homogeneous part, which had the 2 constants of integration, where that's where the initial conditions came in, and then we just had to guess a particular solution as well. What if instead there was a negative sign initially? So it's x double dot equals negative 3x. Well, in this case, it looks like it's x double dot plus 3x equals 0. The auxiliary equation then looks like it's x squared plus 3 equals 0. Or that r equals 0 plus or minus the square root of 3 times I. Because I ultimately have to take the square root of a negative number. In this case, both of the r values are distinct, but they're complex. You can remember we were writing this as gamma plus or minus delta times I. So it looks like gamma has a value of 0, delta has a value of negative 3. And the homogeneous solution in this case, then we said, was there's an overall exponential e to the gamma times t, which then looks like it's just going to be 0 times t, so exponential is going to go away. And then we had some constant times cosine of delta, which was the square root of 3 times t, plus some phase angle. So it looks like then the solution is just some constant c, cosine, square root of 3 times t, and then there's a phase angle phi. X dot, then looks like it's negative c, square root of 3, sine of square root of 3t plus phi. And this isn't too hard for the same initial conditions. X at 0 looks like then it's c times cosine of phi, and that better be equal to 0. Well, there's 2 ways this could happen. C could be 0, but notice if c is 0, the entire solution is 0. And that's probably not going to be the case, particularly since the first derivative has a non-zero value. That is a possible solution where just x equals 0 for all of time. But it's going to be hard to make the second initial condition match that. So then that suggests that cosine of phi better be equal to 0, which then suggests that phi better be pi over 2. Then the first derivative, when I plug in 0, I get negative square root of 3 times c. Sine of phi equals 1. Phi, or sine of pi over 2, is equal to 1, because we've already figured out phi. So then that suggests that c is going to be negative 1 over the square root of 3. So at the end of the day, x sub t looks like it's negative 1 over the square root of 3 cosine of square root of 3t plus pi over 2. But unsurprisingly, by trig identities, cosine of something times plus pi over 2 is negative sine. So then this becomes 1 over square root of 3 sine of square root of 3 times t. It is something that oscillates back and forth as just a simple sine function. So let's wrap up back to the physics. And then the next module will just be a bunch of examples. We have the simple harmonic motion differential equation. We could solve this, and the auxiliary equation would give that r equals 0 plus or minus omega naught times I in this case. Again, why? Also, this is motivating why we chose omega squared, because we knew we're going to take a square root at the end of the day. So they're distinct, particularly it's complex. So we know that then the solution is going to look something like a cosine of, and it looks like omega naught is playing the role of delta times t plus some phi. So we know then that the solution looks like a trig function, where a and phi are your constants of integration that you have to then solve for, given the initial conditions. Since this is physics, there's some physical representations of what these symbols mean. A is the amplitude of the motion, how far away from this kind of equilibrium position, which in this case is just the origin. This is the phase angle. Then omega t, notice it does indeed play a role of some sort of angular velocity. Or again, for the box on a spring, remember that omega naught was k over m, square root of k over m, for a box on a spring. For a pendulum, it's not k over m, it's something else. It probably involves the length of the pendulum in g, since it's gravity that's doing all the motion. Again, we'll see that next time. What are some various properties? Well, I could ask, what is the period of motion? How long does it take before things start repeating themselves? Well, I know for a trig function that the cosine and sine have a period of 2 pi. So it's whatever time it takes to go from, say, t equals 0, which is then going to be how much time it takes to go from the inside of the trig function to some new value where that amount has increased by 2 pi, where the entire thing has increased by an amount 2 pi. So in this case, it looks like then the period is just 2 pi over omega at the end of the day. Or if we're doing box on a spring, 2 pi, right, since divided by omega naught, m over k in this case. And notice it's independent of the amplitude, whereas independent of a. Doesn't matter how far away from the origin it is, the period is still the same whether it's just a tiny little displacement or whether it's doing a big old displacement around the origin. It's independent of the amplitude. So that's a good one. I guess we've transitioned to red. All right, period of motion. And then you can do things like, the velocity. Looks like then it's negative a omega naught sine of omega naught t plus phi. And you could ask, when is the velocity maximized? Well, the velocity is maximized when the trig function is 1 or minus 1. So it looks like V max is going to be omega naught times A. And it occurs at the equilibrium point. Right, think of a pendulum. It's moving fastest when it oscillates through that bottom point before it starts to rise again. And again, that's just math. You can work out. Then the acceleration, take the derivative again, a omega naught squared, cosine of omega t plus phi. But then notice if I rewrite this thing out front as negative omega naught squared times, and I'll put all this in brackets, a times that whole cosine mess. Well, that thing in the brackets is just the original position, right? That this is just negative omega naught squared times x of t. As must be the case, because remember, a is the same thing as the second derivative, And this is just returning back the differential equation. Which, again, if this is supposed to be a solution to the differential equation, this is not too surprising. All right, so with the differential equations class, hopefully a lot of this was review. But we're, again, particularly aiming to be able to solve, whenever you see that equation, jump for joy, because it's simple harmonic motion. And we'll do some problems next module.